Okay. So let us start today's session.
Yes, sir.
So this will be on processing of non-metallic materials. In the first question, uh, it is like again to match the followings, where there are different kinds of polymers and some additives of polymers, and we need to match which one characterize which one, right? So if you see these polymers are basically composed of like atoms of carbons in combination with other elements, right? And mainly there are, if you see, there are what are the different kinds of elements? If you see, there are hydrogen, carbon, nitrogen, oxygen. Maybe there can be silicon, some sulfur, chlorine. These basically these elements are can be present in the polymers. So there are two different kinds of polymers, as we all know, uh, thermosetting and thermoplastic. So thermosetting plastics and thermoplastics, uh, they behave differently when exposed to heat, right? We have discussed it earlier also. So thermoplastics can melt under heat after curing, while thermoset plastics retain their form and stay solid under heat once cured, right? Uh, because thermoplastics have low melting point, they are ideal for applications where we want some recycling. So if we write it here, uh, thermoplastic materials can be recycled and thermoset recycling not possible, right? And thermoset plastics, in contrast, they are able to extend kind of high temperatures without losing their shape and making them more durable, right? And aesthetically, if you see, thermoplastics are seen as superior to thermoset polymers. However, thermoset materials are still deemed to have better aesthetics than alternatives such as metals, of course. So, if we see in terms of aesthetics, so thermoplastics are much more aesthetically better than thermoset than metals. And maybe both the materials, these thermoset and thermoplastics, they allow for uh, in mold painting or coating, or maybe you can do some kind of spray coating directly into the mold before these polymers are injected into it. And yeah, and this injection technique offers better adhesion to the material, and it can prevent like chipping or flaking even under harsh weather conditions. So thermoplastic polymers here is it is matching with heat forming, and thermosetting is heat setting, right? And you can add different kinds of additives to impart, maybe to improve the moldability, to improve the properties of the plastic itself. uh, Additives can be used like fillers, like lubricants, coloring agents, stabilizers, antioxidants, flame retardants. These things can be used to enhance the property of the plastic. So if you see different kinds of additives, basically fillers are used to enhance the mechanical properties. Um, it can reduce the shrinkage when it is getting cured. It can reduce the weight also. Uh, there is something called plasticizer which increase the flowability or flexibility when it is getting heated. So plasticizer is here. It will be matching with it increases flexibility and flowability, and then you have lubricant which can improve moldability and maybe extraction from the mold. So after getting cured, when you want to extract the final product from the mold, lubricant always helps. It can reduce the friction with the mold wall, right? And you can use coloring agent which can impart color. You can use stabilizer uh, which can retard the degradation due to maybe heat or light, these things. And antioxidants can be used to retard the degradation due to oxidation. So antioxidants are used to retard the degradation due to oxidation. And there also can be flame retardants which can reduce flammability. So these are different kinds of additives, as I was mentioning, which you can add with plastics to enhance its different properties, right?
So,
So moving to next question, we need to find out which of the following statements are correct. So the statements are: plastics have good corrosion resistance. They generally do not obtain good surface finish. Amorphous polymers are cooled below melting temperature, and crystalline polymers are cooled below plus transition temperature. So in terms of properties, plastics are basically one is lightweight. Yes, it is having corrosion resistance. It have good corrosion resistant property. So this is true. And then surface finish is very good. So this statement is false, and it can have good formability also. So these are kind of different properties of plastics. Uh, if you see welding techniques of plastics, this plastic welding is process of joining two pieces of thermoplastics at heated state maybe and under a pressure. And because of this elevated pressure and temperature, there can be some kind of cross linking of their polymer molecules, right? So, and this is how these workpieces are fused together. You can add with you can add filler material, or you cannot add filler material. So this can be fused with or without filler material. And the joint forms when the parts are cooled below the glass transition temperature for an amorphous polymer. So if it is amorphous in nature, you should cool it faster, at a much faster rate. Below glass transition temperature. And it is, if it is crystalline, so cooling can be slower and cooled below melting temperature. So what are these statements saying? It says that amorphous polymers are cooled below melting temperature. This is false, of course. So for amorphous, it is cooled below. It, it should have cooled below the glass transition temperature, and for crystalline, it should be cooled below the melting temperature. So only the statement one is correct here, right?
Yes, sir. Yes, sir.
Any question till now?
Sir, they can indicate the glass transition temperature.
I couldn't get you. What was your question?
Sir, they can indicate the glass transition temperature.
What is the best transition temperature, right?
Yes, sir.
So it is like let us try to understand. I need some blank space actually. Okay, can we write here? Uh, Let us try to understand. Maybe in terms of metals. So glass transition temperature can be in polymers also, in metals also. So basically glass transition temperature is, let me define it in this way. Uh, Whenever there is some kind of liquid formation, so if you are hitting a metal, there will be liquid formation. If you are hitting a polymer, there will be liquid formation. And if you somehow cool it in such a way that that whatever properties liquids have, it can sustain that property in its solid state also. So uh, maybe we can try it in terms of a graph also. Let me try it in terms of graph. So let's say this is time and this is temperature. I hope you are aware of this TTT curve
Yes, sir.
in your metallurgy thing. So let us say initially we are somewhere in liquid state here, and if you want to make some solid from this liquid, there will be some kind of C curve here, right? So there will be here it will start the formation of crystalline, and here it will finish the transformation, right? So if you can somehow control your cooling in such a way that it it is not crossing this path, this start of this onset of this crystalline formation, you can retain the property of liquid itself. So whenever you are forming some kind of crystalline structure itself. they form some kind of intermetallics, right? I'm talking in terms of metals here, not in terms of polymers. Uh, but if you control the cooling in such a way, if you can make it much faster than the conventional one, you can come some kind of microstructure which can be very much hard and brittle also. So here also, if you see this glass and maybe ceramics, those are also kind of high temperature sustainability is there. They are hard in nature and brittle also, right? So it's all because of this controlling the cooling rate. You got my point?
Yes, sir.
So there are two kinds of materials. If you go through it, one is crystalline, where you will have some kind of defined slip lines, defined slip planes, and you can get the desired orientation of deformation. So slip planes are the most favorable planes where deformation takes place, right? So one is crystalline, and there is another one which is amorphous or glass-like material. So glass transition temperature is that whenever if you can somehow can sustain the property of the liquid itself in its solid state, that temperature is called glass transition temperature.
Okay, sir.
Okay. So moving to question 3, um, there are different welding techniques, where one is RF welding, which is radio frequency. There is ultra short pulse laser, and some grinding of thermoset polymers, which you need to match with the other columns, right? So there are different kinds of plastic welding techniques, as we know. Uh, you have gone through that lectures also. So there is ultrasonic welding, where the welding cycle can be like 1 second only. There can be kind of frequency or vibration of the horn, which can be of range of 20 to 70 kilohertz, and some amplitude of that vibration, and then it is generally used for processing amorphous polymers, or maybe polystyrene, or yeah. So there is ultrasonic welding, and FSW also can be used to join polymeric materials, namely polypropylene sheets. So FSW have been used till now. Maybe it has not been explored for other kind of polymeric sheets. So as of now, it has been used for polypropylene sheets with FSW. And then in radio frequency welding, it is like there will be internal regeneration by dielectric losses in thermoplastics, and then rapidly changing the electric field uh, results in intermolecular friction, and because of those friction there can be heat generation, right? And cycle time again is very less, like it can vary from 1 to 5 seconds, and it is relatively very fast process, and generally this is used for thin sheets. So this RF welding is generally used for thin sheets of maybe 0.03 mm to 1 mm, and basically the basic thing is material should have high dielectric losses. right? And using additives and consumables, the non-polar materials can be sealed with RF welding, and other improvements include this machine design with automatic tuning of power supply and quick changeover of cooling. These are few application of radio frequency welding. So here this is dielectric hysteresis losses. So RF welding is the basic principle is dielectric loss of polymer material. And then there is ultra short pulse laser welding, where lasers emit laser pulses with extremely short pulse duration, typically in the range of femtosecond to picosecond. And because of this lower pulse duration, there will be very high peak power density, which is obtained. And main process parameters of these ultra fast pulse lasers are this pulse duration. Let me take another color. So this is, there is pulse duration, which is in the range of femtosecond to picosecond, right? And energy per pulse is another parameter, which can be from some nanojoule to millijoule. And pulse frequency can be another parameter, maybe from some kilohertz to megahertz. And then there is average power of the machine itself. So it can vary from uh, maybe in terms of some 100 watts, right? And if you see the different kinds of materials which used for welding, in ultra short pulse laser welding, there are different glasses like fused silica, like borosilicate glasses. Uh, these are kind of different materials which are used in ultra short pulse laser welding. There can be biomedical applications also, and yeah, there is rapid prototyping and microfabrication application also for this ultra short pulse laser welding. So here, for this sake of question, uh, this is matching with this one, extremely short pulse duration. And then if you see machining of plastics, grinding of thermosetting plastics with normal conditions. So this is kind of thermoset plastics grinding are little bit difficult because of their low melting temperature. So, and during grinding, there will always be clogging of this abrasive wheel. It is always a problem. And grinding wheel with open grain spacing with an excess of coolant to, it is used to prevent this overheating and wheel loading, right? And yeah, so for grinding sake, clogging of the abrasive wheel is the main problem. And you can always use different coolants if the, if you are heating the material to such high extent, right? So cooling can be always used to prevent overheating. And if you see this machining of this thermoset polymers, so when this is in cast from uh, it is having brittleness like that of glass or ceramic, and it is prone to form easy crack during cutting. So whenever you are doing some machining, normally discontinuous chips with like smooth fractured surfaces and large thickness is obtained. And whenever you are getting some kind of discontinuous chips, your tool rake angle will be positive, right? And the mechanism, if you see, this is kind of elastic fracture without plastic deformation. That means your material doesn't go into your plastic state. It's in the elastic itself. It is fracturing, right?
Yes, sir.
Moving to next question. This is a generalized question, like which one of the following techniques are used to join plastic to metal? So there are different kinds of welding techniques where resistance spot, laser, explosive, gas welding, adhesive glues. So before coming into which techniques are useful to join polymers to metals, uh, we should understand why these kind of joinings are useful. So there is demand on dissimilar material joints which have been increased from the viewpoint of design requirements. Maybe there is energy consumption point of view, there are environmental concerns, cost savings are also there. So metals usually have been selected since they have superior properties like high ductility, high thermal conductivity, high machinability, where for plastics they offer high corrosion resistance, good insulation property, they are lightweight. So dissimilar material joints between polymers and metals can be obtained from both the two different properties at the same time. And technical difficulties during these joining techniques arise because of their dissimilarity in mechanical, thermal, and chemical behavior, right? And for polymers, metals, hybrid joints, we can use various joining techniques such as there is of course this adhesive bonds or adhesive glues, or we can use some kinds of mechanical joining like bolts and rivets. So use of adhesive bonding for joining aluminium to polytetrafluoroethylene is like this is in as of now this is in market, and it is successfully achieved only after treating that polymer material surface with sodium, right? And there is like bolted joints of carbon fiber reinforced epoxy and titanium, that is also in already the research has been done, and that results in an increase in joint strength, but there is some drawbacks like long processing time, high production cost, and limitation of shape and size which are identified. Now, these adhesive bonds for joining, they have problems in terms of environmental restriction on the emission of, they can emit uh, kind of volatile organic compounds, and so mass production is kind of difficulty here. So to improve the quality, production time, and reliability of this dissimilar material joint, uh, people use this laser beam welding or resistance welding to some extent, and those have been used to join plastics to metal. So in terms of fusion bonding, of course, this laser and resistance welding are kind of fusion bonding. And in terms of fusion bonding, particularly this resistance spot welding, when it is applied to this uh, polymer material, this has been proven to produce close to parent strength joints. So for resistance spot welding, has been proven to produce close to per instance joints and in short processing times. There are some additional advantages like you can do some kind of automation, you can do some kind of online monitoring. These are additional parts, of course. So yeah, in for this question, yes, resistance spot welding is used, laser welding is used, adhesive glues are used. So one, two, and five, right? Any question?
No, sir.
Okay. Let's move to the next question then. We need to arrange the following processes in proper sequence for manufacturing of glass. So, for manufacturing of glass, the first and foremost, the first one is melting. So, initially you will be starting with from the liquid state, right? And here you need to mix the raw materials in proper proportions. So, there can be sand, there can be limestone, there can be soda ash, and they are mixed and finely powdered and kind of homogeneous mixture are prepared, and then they are fused with some broken glass, and they melts and fuses at maybe 1800 degrees C. And so basically there will be the first step is melting, which is done at which is done at 1800 degrees C. And then there is forming or shaping maybe. So in forming and shaping, what we do is like molten material is converted to your desired shape, maybe by blowing or molding or pressing between rollers. So desired shape is obtained. And then you can do some kind of annealing. What we do in annealing is, as it has already been discussed, in annealing, you cool it gradually at room temperature. The longer the annealing period, better the quality of glass finishing. So annealing period longer, glass finishing is better. And after annealing, it is subjected to some kind of cleaning, polishing, cutting, and also sandblasting also. So uh, this is your first step, and then this is your second step, then this is your third step, and this is the final one. Okay. In the next question, we need to find out which of the following statements are correct. These are all in from the glass material. So if you see, glasses have a melting range which is called glass transition, as I was saying. When hitting the solid material into this range, it will generally become softer and more flexible, and when it crosses through the glass transition, it will become very thick, sluggish, viscous liquid and become sticky, honey-like. And so welding can usually take place by simply pressing these two melted surface together, and the two liquids will generally mix and join at first contact. And upon cooling through this glass transition, the welding piece will solidify as one solid piece of amorphous material. And basically, how we do heating is we can use some kind of gas torch or furnace, because the temperatures for melting glass are often quite high. And these temperatures may vary depending on the type of glasses also. So if you see, lead glass becomes weldable liquid at around 870 degrees C. There is quartz glass which is fused silica that must be heated over 1650 degrees C. And sometimes you can attach some kind of tube allowing it to be blown into various shapes, like uh, like the way you want to form it. And when two pieces of this liquid glass are placed together, they will usually weld very rapidly, very readily. And as glass is very brittle in its solid state, they are often prone to cracking upon heating and cooling, right? And this is because of its brittleness of the glass, and it doesn't allow uneven thermal expansion. So yeah. And this welded glass need to be cooled very slowly and evenly through the glass transition in a process called annealing, as I was saying. So here the statements are: upon cooling through the glass transition, the welded piece will solidify as one solid piece of amorphous material. This is true, of course. Glass becomes a weldable liquid at around 870 degrees C. This is also true. And there is another kind of glass which I have mentioned. Must be heated over 1650 degrees C. And it says that glass is ductile in nature in solid state, which is of course false. And annealing of welded glass is used to relieve any internal stress created by temperature gradient. Of course, this is true. So in any kind of heat treatment like annealing, it is used to relieve the residual internal stresses which is created by temperature gradient, right? Now, in the next question, it asks which one of the following joining process is used to join ceramic parts. So, electron beam welding, laser beam welding, friction welding, diffusion welding, these techniques can be used to join ceramic parts. And if you see in electron beam welding, high beam energy is restricted to small ceramic parts. That can be used only for these ceramics with defined melting points like Al2O3, but not for SiC and Si3N4. So Al2O3 have defined melting points, and high stress is caused by this severe temperature gradient, which can easily damage the ceramic joints. And ceramics basically can be joined to themselves or to metals by diffusion welding. So it is complicated to apply the necessary pressure for larger components. There can be high equipment costs and long joining times also, which lead to high production costs. So in terms of economical joining process, brazing is always there. So brazing is most economical process for ceramics. Uh, you can use both metallic and ceramic brazers where it is useful. So electron beam welding is used, diffusion welding is used, laser beam welding is used, and you can use friction welding also. Now, this is again a generalized question. Which of the following properties ceramics have? So, in terms of ceramic properties, they always have high temperature resistance. So, it can sustain a lot of temperature. Even while processing, it can sustain a lot of temperature. And it is extremely hard, but they have low electrical conductivity. So, generally, it is used for thermal insulation property, and in terms of chemical resistance it is also high, and the density is lower compared to metals. So in terms of properties, they have high temperature resistance, they have extremely high hardness, then they have low electrical conductivity, then they have high thermal insulating property, then they have high chemical resistance, and then lower density compared to metals. So, this is the last question. So, in question 9, it says which of the following statements are correct in terms of machining of ceramics. So, if we see in machining of ceramics, application of conventional machining process for the ceramics are very difficult for its brittleness. So, machining cycle times are longer for harder materials, of course. Generally, grinding and ultrasonic assisted machining technology is more suitable for ceramics and glass kind of materials. You can use laser micro machining also, which are also being developed, and ultrasonic processing like it helps to reduce the subsurface damages. And if you want to obtain some kind of good surface finish, uh, people use lapping and honing and polishing techniques. These are always there to obtain good surface finish. So here the statements are: grinding and ultrasonic assisted machining technology is not suitable for ceramics and glasses. This is suitable, of course. This is false. Then it says application of conventional machining process are difficult for brittle and hard ceramics. Yes, conventional machining process are difficult for brittle and hard ceramics and or glass materials also. And for good surface finish, to obtain good surface finish, you need lapping or honing. So micro machining, of course, is a machining technology. This is not used for surface finish. Okay, that's it from my side.
Sir,
Is there any question?
sir,
Yeah.
sir.
Hello.
Yeah, sir, can you say about the grinding of the ceramic and glasses? Like whether it is possible or what are the drawbacks and advantages?
For grinding, what?
Yes, sir, from grinding.
For grinding of ceramics and glasses, what was your question?
Yes, sir, the last question,
Yeah. So
so
I had mentioned like it is not suitable. Uh,
yes, sir.
so
So if it's suitable, then what is the disadvantage of grinding? Even if it's suitable.
uh, can you come a little bit louder?
Sir, though grinding is suitable for machining of ceramics and glasses, what are the disadvantages associated with grinding, sir?
What are the different techniques which are useful for
Disadvantages.
the disadvantages for machining of ceramics?
Yeah, yes, sir. Like we said, in ultrasonic assisted machining, and there will be subsurface. So similarly for grinding.
Uh, okay, let me think about this. Disadvantages of like the main disadvantages is of course the ceramics are very much brittle in nature, so you cannot give a kind of impact force or like high tool force that should not be used in ceramics. That is the most disadvantages while machining this ceramic object. Basically, this operation should be carefully done to avoid damages. And in terms of grinding, what is the disadvantages of grinding? Maybe it cannot remove high amount of material. So for grinding, whenever you are doing some grinding, it only removes a little amount, right? So material removal rate is very lower, and for removing required amount of work material, it consumes more time. anything, any more disadvantages of grinding, I'm not sure at this point of time.
But it is still possible, right, sir, for grinding glass and ceramics.
Grinding. This is the most suitable operation for ceramic thing, grinding and ultrasonic assisted. So if you are doing some conventional machining, if you are using some kind of tool and you need to apply some cutting force, and because of applying those forces, maybe this there will be damage of this material.
Yes, sir. So grinding is suitable for ceramics, and also ultrasonic assisted machining, and also laser micro machining is also suitable, or it is not suitable, sir?
Yes, laser is suitable. So this is a recent development for ceramics.
But amongst all these, we go for lapping and honing for good surface finish.
Good surface finish. Yeah.
Okay. And sir, I have another doubt, sir.
Sorry.
Sir, I have another doubt regarding same
Huh.
grinding, but with respect to like thermosetting polymers. For like we said that the clogging will happen that while grinding of
Huh.
polymers. So we go for different setup of grinding fields. Like it should be much more open and all those things. But what is the reason for that? This one, sir, the clogging problem. Is it because of the high speed generation, or it is because of the, uh, the
Okay.
softness of the glass? What can we say on that, sir? Like how the clogging is arising, and what is the requirement? Why are you using the coolants for while grinding the glasses?
So where was the question? Yeah. Let me think a little bit. So your question was why this clogging happens and how you can prevent.
I said, what is the reason for this clog? Is it because of the low melting temperature, or
So it
is it?
is yeah, clogging is of course mainly for this overheating of this material, which whenever you are producing some chips, it causes the chips to embed into that grinding wheel, and as a result it commonly referred as clogging of that adhesion of that chipping material into that grinding wheel. Yes, of course this is because of this overheating of the material.
Yes, and can we say is it because of its lower melting temperatures, or is it a reason behind this?
So for thermoset polymers, it is high, right? The melting point.
Yes, sir. That's my doubt. So
So if the melting point is higher, so if the melting point is higher, when you are doing some kind of grinding, so maybe you can think it is in this way. It is sustaining that much of temperature. So and during the temperature, whatever chip formation is there, these those are getting adhered into the abrasive wheel. So if the melting temperature is lower, it is easier to grind, na. So means soft materials it's easier to machine, of course.
Yeah, okay, sir. Now I get it.
है ना?
Yes, sir. Yes, sir. I understand.
Yeah.
Yes, sir. That's it, sir. Doubts.
That's it.
Yes, sir. Clear, sir.
Okay. Let's end this session here.
Yes, sir.
Okay. Thank you.
Thank you so much, sir.
Bye bye.